Hello, hello. Hi, everyone. Welcome to day two of our unit two material. We're gonna go over differentiation rules, and then we're gonna go over what are we gonna go over? I already forgot. Let's see. We are going over derivatives as rate of change. Okay, so let's get started. A bit of a warning. We have two visitors in the video. They are my cousin's cats. We have a cat named Muta and a cat named Salem. I don't know if they'll make an appearance, but we'll see. They am currently on a table that they like to get onto, so we'll find out. Okay. Um, let's get started. So right here, we're gonna learn some simplification tricks that are going to help us with differentiation. Let's start off with some review material. First, rules of exponent. Let C be a constant. This C over a to the power of m can be rewritten as C times a to the power of negative m. And then don't forget that a root, oh, sorry, that was not in frame. And don't forget that a root can be expressed as a power. So for example, the square root is 1 over 2. We're not going to get too into this idea, but it's the nth root can be rewritten as x to the power of 1 over n. Then we have the constant rule, which is something we lightly discussed in one of our last videos, where if the function is just a constant function, then it doesn't matter what input you put it, they're both going to be that constant. And we see that that constant minus that constant will be 0. 0 divided by h is 0. So you don't even have to take the limit if you're doing a derivative of a constant. It's just going to be 0. So that's the biggest implication, is that if f of x is some constant, then f prime of x is 0, 1. The f prime looks ridiculously large. Okay. All right. Then we have the constant multiple rule. If c is a constant, then if we're taking the derivative of a constant multiplying that function, you could technically get away with letting it escape. If you were to perform it with the function anyway, you should still get the same result. But in some cases, we might want to take this advantage of this trick. Or if you wanted to see it in this way, if we have some function j that's technically just a constant times that f function, then you could argue that j prime is equal to c times f prime. Basically just a different way of notating how this occurred. Now we have the power rule. So this is going to be our first set of rules where we're going to learn how easy tricks of differentiation. So we're not done with limits necessarily, but we are moving from expressing limits as slopes of a tangent line into just their differentiation technique. So we have one differentiation technique that is the power rule. So let n be a positive integer. If a function is equal to some constant times x to the power of n, then its derivative is the constant times n times x to the power of n minus 1. So what we talked about on our worksheet from day one is at first when you provide with x to the power of n and you take a derivative, you bring the n down and you subtract 1 from x's power. So instead of doing all of these with the limit definition of a derivative, let's find the derivative of all of these using the power rule. Here, we should do some rewriting. And we know that this f of x function in particular can be expressed as x to the power of 1 over 2. So, what do? Well, we bring this down for f prime's construction, I mean. We bring this down, and then we subtract 1 from this power. So, 1/2 minus 1. Well, what that's going to be negative 1/2. And then remember, with negatives, we can jump it over here to the bottom of a fraction. And that can be written as 1 over 2 square root of x. Now, not that you don't believe me, but we did this problem yesterday, or not yesterday, well, yeah, I guess yesterday. Day 1, right? Um, where is it? It's over here. See how we got over here? But here we got the hard way. Here, we're getting it the easy way. F prime of x is equal to 1 over 2 square root of x. All right. How about over here? So over here, for f prime, we simply just bring that power down and minus 1 from that power. So f prime, for this example, 2 is going to look like 2, because it's the constant in front of it, times negative 4. Sorry about that sneeze. Times that x still, but 1 minus this power, so negative 5. Here you could simplify it a little bit. You got negative 8, x to the power of negative 5. And if we don't like negatives in our powers, we can just rewrite it like this. Okay? Over here, you drag that power down. And then subtract 1 from its power. So instead of 10, we write 9. This doesn't have too much of a simplification. It's really just 30 x to the power of 9. And then over here, we have this derivative. And we're going to go ahead and... Oh, actually, we should rewrite this just a little bit so it's a bit more palatable. And now we can go ahead and just easily use the power rule. So 5 times negative 6 times x to the power of negative 7. And that can be written as negative 30 over x to the power of 7. Okay, I hope you're following along with me so far, and I hope you're not cursing at me too much for if you were annoyed with the limits idea and how we can just jump into this power rule idea. Let's keep it going. We're almost done. Just rewriting that. We have 2 times that negative 3, x to the power of negative 4. Rewrite this again, negative 6 over x to the power of 4. And then last and not least, we have 3x to the negative 2. F prime of x is equal to negative 6. Or, I'm skipping a step. 3 times negative 2 times x to the power of negative 3, and you get negative 6 over x to the power of 3. All right. So far all these rules are pretty straightforward. It's just that neat little pattern with powers. These aren't all the rules. We're going to learn more rules. Let's learn more rules. We're going to talk next about the sum and difference rules of differentiation. Let C be a constant. If we have, well, I think I copied and pasted that too furiously, yeah, because technically we don't have any presence of C. But either way, if I'm taking the derivative of a function plus or minus another function, technically this is just that derivative of the first function plus or minus that derivative of the second function. Or more plainly, if I have a function that can be described as the sum or the subtraction of two other functions, then its derivative is equal to the derivative of that first function plus or minus the derivative of that second function. So we're going to be set up in a situation where we have to use this rule. Example 7. Find f prime for this function. And notice it's the combination of three parts. So instead of us sort of tackling them all together, we could technically just tackle them all piece by piece. Now, please keep in mind that you are only allowed to do this because they are adding and subtracting. We're going to get into it today, where although this pattern of of differentiation seems like distribution, it is not always the case. Please keep that in mind. So, after splitting it up because of the sum and different rules of differentiation, we just perform these derivatives piece by piece. We get 6x squared minus 12x and then plus 0, which we technically, excuse me, I had to mute because of the sniffling, which we technically don't have to write. Oh, actually no, let's write it plus 0. So correlating that and that. Obviously here there's no simplification. This is your answer for that f prime. Now that's all to say that you could technically have still done this with the limit definition of a derivative, but we're learning these tricks. Right. Now using these tricks, we're going to revisit an old layout of a problem. This problem reads, find the equation of the line tangent to f of x squared minus 4x plus 6 at x is equal to 1. Well, recall the idea of that line tangent. We need to know where does it lie. So we need to still find f of 1 since we know that we're going to be at x is equal to 1. So that's 1 squared minus 4 times 1 plus 6, which is just 1 minus 4 plus 6. And that's going to be 3. So we know that our coordinate is going to be 1, 3. Now, recall that we said that the slope of the tangent line is equivalent to the derivative at that specific point. Well, we know that in our case, this specific point is 1. But instead of defining f prime of x as its limit, we're actually just going to go ahead and provide it as its function using the differentiation rules. So we have, via the sum and difference rules, we have that is just the derivative of x squared minus the derivative of 4x, and then plus the derivative of 6. And you have 2x. What comes out of here is a 4, and then what comes out of here is a 0. Now, after having this derivative function, we still need to find f prime of 1. So just plug in 1. 2 times 1 minus 4, that's going to be negative 2. So your slope is negative 2. Now we just need the equation. So y minus y1 is equal to m times x minus x1. Plug in everything. We know that y1 is 3 in this case, m is negative 2 in this case. And then x1 is 1. Distribute that negative 2 And then let's add that 3 to get just a y equals by itself. And that's the answer. Okay, another set of tricks. Now, this is important because this is what I was referring to you guys when I was telling you that some of these patterns that look like the distribution of a derivative is a coincidence. And we're going to see that play right now. Or more specifically, a derivative, right? Separate under addition and subtraction. But we have a different approach for multiplication and division. So first is, or here, let me write that this is not part of the answer. Okay, the answer from example 8. So this is going to lead us into the product rule. The product rule states that let f of x and g of x be two differentiable functions. If we want to find the derivative of this function times this function, it's going to lead us into this pattern. In this pattern, we use f of x and g of x. They actually remain untouched. But then we use f of x prime and g of x prime. And they sort of have this like sing-song, maybe looks like even foil-esque method. You can see that here, or let me use colors. We can see that here we get one f of x with a prime, one f of x without a prime. Here we get one f g of x without a prime, one g of x with a prime. And it's important to note that each of these guys have one prime each. So you can sort of just have that mentality. Let j of x be the be the product of two functions, x squared plus 2x and 3x squared minus 5x. Let's label this f of x, and let's label this g of x. So if we label that f of x, then we know this is going to be f of x, and this is going to be g of x. Now, we're going to go ahead and do the derivative of these guys each. Derivative of f of x is 2x, or wait, I'm skipping steps. Sorry, I'm like already so used to the trick. It's going to be x squared prime plus 2x prime, which we know is just 2x, and then that's 2x over here is going to be just 2. A similar feature occurs here. We know derivative of that is going to be 6x, and derivative of this is going to be 5, but it's minus in front of it, so minus 5. And then we're going to go ahead and just make this layout. We have f of x prime times g of x plus g of x prime times f of x. And you get 2x plus 2 times 3x squared minus 5x plus g prime, which is 6x minus 5, and times f of x, which is x squared plus 2x. And that would be j prime of x. So we just use the product rule. The product rule does not mean that you find the derivative of f and g and then multiply them. They have this little pattern where we have to first acknowledge what's f of x and what's g of x, and then we have to do those primes individually, and then do the product of one with the prime, one without the prime, and then the other one with the prime and the other one without the prime. Keep in mind this combination of a prime, no prime, a prime, no prime, FG, GF. Okay. We're going to do a couple, or no, I'm sorry, we're going to do one more of these and then we're going to do a new rule. So let's do example 10. We set let j of x be the product of this function times this function. What's j prime of x? Okay. So again, we can label f of x as that first guy here. Keep in mind your choice of f of x and g of x shouldn't matter. It's going to be the same under like the cumulative properties of addition and subtraction. So just keep that in mind in your labeling. So we're labeling this f of x and this g of x. Let's find f prime. This one. I still want to just practice for a little bit using the rules. Maybe for the next one we don't use the rules piece by piece. It's 2x to the power of 5 prime minus 3x prime plus 1 prime, which is just 10x to the power of 4 minus 3 plus 0. Over here, we see that's going to be 3x squared minus prime minus 5x prime. So it's going to be 6x minus 5. Give me a second. I need to blow my nose, and I don't want to do that on camera because that's probably going to be really gross for you all. Or not on camera, but on mic. Um, Random, but I am allergic to cats. So, and I took an allergy med before the video, but clearly the allergy med's only doing so much. Okay. Anyways, not the point. And then we just do the setup like we did before. G prime of x is equal to, let's do these two first. We got 10x to the power of 4 minus 3, and then times 3x squared minus 5x, and then plus, I accidentally ran out of space. Let's just do it here. 2x5 minus 3x plus 1 times 6x minus 5. All right. Next is the quotient rule. Now here, the order is going to matter. Let's say you have it to where one function is divided by another function. So the setup becomes you do the derivative of the first guy, combine it with g, or multiply it with g, minus derivative of the second guy, combine it with the first guy, f, and all divided by that denominator squared. So here we have an maybe not a new step, but a fifth term to consider. G of x squared, which in reality, I'm not going to get too into that because we should know at this point how to square, but let's just practice this problem because this is new. So I put our efforts towards this. All right, similar idea though, however, now there is only one thing that is f of x and one thing that is g of x here. F of x, via this definition, is the top part. So 5x to the power of 3. And g of x is the bottom part. So 4x squared plus 3x. What's the prime of f of x? Well, that's just going to be 15x squared. What's the prime of g of x? It's going to be 8x plus 3. And now we just plug it in. We have f prime first times g of x, or actually it's written in reverse, but again, multiplication, you can swap them, but we just still have to make sure that either way that first part has f prime g. Some people get confused and they'll want to do g prime f, which is technically not the same thing. 5x to the power of 3 times g prime, which is 8x plus 3, divided by g of x squared. So 4x squared plus 3x squared. And that's going to be jx prime. Let's go ahead and keep this going with some simplification ideas. So here we have f of x is clearly 3x minus 1, and g of x is 4x plus 5. The derivatives are 3 and 4, respectively. And we're going to go ahead and do all of this. We have j prime of x is equal to 3 times g of x, which is 4x plus 5, and then plus g prime, which is 4 times f of x, which is 3x minus 1. All divided by g of x, or x plus 5 squared. Okay? Well, from here, we can go ahead and multiply this. 12x plus 15 plus 12x minus 4 over 4x plus 5 squared. Okay, that's going to be 24x plus 11 over 16x squared plus 40x plus 25. Okay, let me just double check my solutions to make sure this is indeed the right one. Oh, I made a mistake. Can anybody tell me what the mistake I made? Well, you technically can't, right? But the mistake I made is that I forgot the subtraction. The formula calls for subtraction in the middle. So it's subtraction. So actually, there's no x's on the top because 12x minus 12x is no x's, but 15 plus 4 is actually 19. Okay. All right. Now that's going to be it for our rules. We are going to learn more rules later, but now we need to hop back into the application sort of portions of these. Okay? Now, the application portion is going to start right about here, but we need to touch base on interval notation ideas. Okay? So, you read from left to right. So we organize numbers from left to right, from the smaller number to the biggest number. So if I'm to start this interval, and I want you all to do this with me technically, because it's going to play into these parts later, -5, then that means the only thing that could be right to it is anything greater than -5. So -4, -3, -2, -1, 0, 1, 2, 3, 4, 5. Parentheses. A parentheses is used when the endpoints is or are not included, represented by an open circle on the number line. The inequalities that reference this is our classic less than and greater than inequality symbols. So, for example, if I want to note -3 to -2 on the interval, I have the option of doing an open circle or a set of parentheses and just color the whole line. Technically, I'm a bit generous with the size of my circles, but you're supposed to color in basically all of 3 up until you actually touch 3. Same thing with -2 as well. Then you have brackets. Brackets are used when the endpoint is/are included. This is represented by a closed circle on the number line. And this are the adjusted inequalities that include that line at the bottom that implies equal to. So if you're going from -1 to 1, you can either choose to do a closed circle and mark that row, or you can do brackets and mark that row. Infinity is, just a recap, infinity is not a number, but it's used in these interval notations. Even though it's used in these interval notations, the key feature is that because it's not a number, in the interval notations, it will always use a parentheses. So, for example, if I'm doing -infinity to -4, and -4 is in closed bracket here or a closed circle here, I'm supposed to just mark all the way to the left to denote that interval. If I want to do the positive side of this, where it's 3 to infinity, that means I could do an open circle or parentheses and mark all the way to infinity to the right. Now, what are the union of intervals? The union of intervals is when the solutions in two different regions on an or when the solutions are in two different regions on the number line. So if this and this are our solution, or is the thing that we're curious about where the answers exist, we say this union this. So keep that in mind. It's nothing too crazy, but it's just a technicality. All right. First application. F prime of A is an instantaneous rate of change at f of x when x is equal to A. One application of derivatives is to estimate an unknown value of a function at a point. In real life, we often know a function's value at some point, like f of A, and the rate it's changing at that point, like f prime of A. And we want to estimate what the function is doing a little farther away, like f of A plus h, with a linear approximation seen here that uses that derivative. So f of A plus h is equal, or not as equal, but is a bit approximate to f of A plus f prime of A times h. For this symbol here, it just means like approximate. It means, to me, I remember learning it like this, and my math teacher laughed in my face, but it was kind of like, I think it's the thing where I was wrong, but I didn't miss the point. So the way I call this, it's like equals. Like you do the hand gesture, like, math, like, like, it kind of equals, right? Let's do a plain example of this though. Given that f of 10 is equal to -5, and f prime of 10 is 6, estimate f of 10 plus, plus, of 10.1. So, we can technically start off with this expression. But in using the estimation, we could first just note it plainly as it's 10 plus 0.1, since we technically know f of 10 and f of 10 prime. So we can, oh, I messed up. We can do the little squigglies and say that it's approximately close to f of 10 plus f prime of 10 times that h. Plug in everything into here. I got -5 plus 6 times 0.1. And then you're left with -4.4 as your answer. So it's not saying that f of 10.1 is -4.4, but it's around, about, can be approximated to -4.4. More application stuff. We want to consider the idea of measuring motion in some sort of plane. Right now, we're just going over it on a line. Okay? Position S of t. S of t tells us where the object is at any time t. Remember, time can't be negative. Velocity. Velocity was defined previously as the first derivative of that position function. But in the context of an application, velocity tells us how fast the position is changing and in what direction. This what direction part is important because if it's positive, that means we're moving forward. But if it's negative, then that means we're going backwards. Speed. The magnitude of velocity, the absolute value. So this is just regardless, or not, okay. You know how like in cars, we just have like a classic speedometer that goes from 0 to whatever. In that sort of realm with speed, we don't care necessarily about reading the speed measurement for what distance we're traveling, if we're going forwards or backwards. We can manually see us going forwards and going backwards. So that's why this is just referred to as speed, but it's for cases where the direction does not matter or the direction doesn't add any valuable input. Okay. Let's do, oh, I missed one. Acceleration. Acceleration is not new, but it is new in this context because, or let me, yeah, I don't think we've talked about acceleration yet. But either way, acceleration is the second derivative of the position function, which, so acceleration is the second derivative of the position function, then that's to imply that the first derivative of the velocity function, here, let me just move a step up. Wait, let me do one step. Let me take out the prime, and then we know that that is just the velocity. So acceleration is the second derivative position function, but it's going to be more referred to as the first derivative of the velocity function. A couple of things that come into play when looking at acceleration and velocity respectively. So we already touched base that velocities has a technicality when it's positive or negative. For all cases when it's positive, it is going forward. It's going forward. And then for when it's negative, it's going backwards. Backward. But it combined with the acceleration idea, we we can have it come into play with the following. In the combination where we're moving forward, but acceleration is negative, that technically implies that we are slowing down. In the technicality, where we are going backward, but the acceleration is increasing, that means that we are slowing down. If we're going forward and the acceleration is positive, then that means we are speeding up. And if we're going backwards, but the acceleration is backwards, then we are also speeding up. So this doesn't necessarily care about the direction, it's just bringing out the technical conflict. If our car, right, is moving forward, but we are decreasing acceleration, then we are slowing down. Similar vibe. If we're going backward, if we were just a car that was stagnant going backward, but we put a little bit into the gas to where technically our acceleration is pushing us forward, then we're slowing down. And then you can see here, this is almost kind of straightforward. If our speed is fast and our acceleration's going forward, then we're speeding up. If we're driving backwards for some reason, but our acceleration indicates that we're accelerating backwards, then we're speeding up. All right, so let's do this application problem. A particle moves along a coordinate axis in a positive direction. Its position in time is given by s of t such that equals t to the power of 3 minus 9t squared plus 24t plus 4. Let t be less than or equal to 0. Wait. Nah, that is definitely a typo. T is positive or greater than 0. My mistake. All right. Find a of t. So just find the second derivative. Let's do velocity of t, which is that first derivative. And this, I'm going to go ahead and just go with my finger showing you what the answer is. So remember, these are all adding or subtracting, so we're kind of just able to do them plainly. Derivative of t to the power of 3 with respect to t is going to be 3t squared. Derivative of negative 9t squared is going to be negative 18t. And then derivative of 24t is going to be plus 24. Now let's do a of t, which is just the prime of the velocity, or the double prime of the position. So this, again, we're able to just do piece by piece. Is derivative first guy, which is just 6t, derivative second guy of 18, negative 18, excuse me, and then the last guy, but we know that 24 is derivative is just going to be a constant, 0. All right, B, or wait, let me box this answer. B, at what time is the particle at rest? More specifically, what are the times that the velocity is 0? So the velocity is going to be 0. We have to go ahead and set this up to 3t squared minus 18t plus 24 is equal to 0. So we have to solve for t in this section. Okay? Well, I'm going to do an easy step where I get rid of my 3's since they're all multiples of 3. T squared minus 6t plus uh, plus 8. And then from here we can either we can factor this a lot of ways. Let's see. I'm gonna go ahead and just use that A times C method we got. Or well, there's no A, so just the C. 8, 1, and 8. Well, it's gonna be they're both negative because the answer. Oh, so 2 and 4. Yeah, okay. So 2 and 4, we got 3 of actually let's do the square, I guess. We got actually no, let's use this. Okay. Negative 2t minus 4t plus 8. Do a split, we got I'm sorry, 3 of t parentheses t minus 2, and then take out negative 4 t minus 2, and oh, let's just do it here. We have 3 factors. We have 3 times t minus 4 times t minus 2, 0, 0. So that means our t's, where the particle's at rest, is 2 and is 4. Now, this tells me that at these 2 points, our particle has the potential to shift. To shift either from being positive or negative. So C says, on what time intervals is the particle speeding up or slowing down? Okay. Well, this is going to be tricky because first we have to acknowledge the aspect of the velocity. The velocity, oh wait, I was going to do prime. The velocity function has 2 roots, or has 2 moments for particles at rest, 2 and 4. So we're to start a number line. Let's start, let me use a different color for this. 0, 1, 2, 3, 4, 5, and then, I'll do it, 6, 7, 8, 9, 10. Then the only times, because because at the end of the day, don't forget we're dealing with the polynomial. The only times that the velocity has a moment to change from either being positive or negative is 2 and 4. So for velocity, we should check its positive or negative values. I mean, we should check values and determine where it's positive or negative. Excuse me, I misspoke. So let's go ahead and check to the left of 2. Let's pick an easy one. Let's pick 1. So V of 1 is equal to 3 1 squared or times 1 squared minus 18 times 1 plus 24. Okay, it's going to be 3 minus 18 plus 24, and that's going to be 9. And 9 is a positive number. Last time I checked. So that means in terms of velocity, it's going to be positive here from 2 and beyond. Or actually, okay, we know that we're dealing with this specific scenario where t can't be less than 0, so we actually know that it's just going to be positive from 0. to 2, but you get the point. Or at least I hope you get the point. Okay. Now we need tests from in between 2 and 4. And the easiest one is just probably going to be 3. So 3 times 3 squared minus 18 times 3 plus 24. That's going to be 27 minus 54 plus 24, which is going to be that I can't do in my head. So let's just do 27. Combine this, that's yeah, so it's going to be -3. Okay, so that means that our velocity is going to be negative from here. And then now we need to check 4 and beyond. So let's just pick 5. 3 times 5 squared minus 18 times 5 plus 24. That's going to be 75 minus 90 plus 24, which is just going to be 9 again. And that means from 4 and beyond, the velocity is going to be positive. Now, this isn't done because we're determining speeding up or slowing down. Speeding up and slowing down involves the velocity and the acceleration. So keep that in mind. Let's now, as a separate note, do the acceleration. But this time we don't have the roots or the root of acceleration, but we can easily figure it out. We know acceleration function was defined as 6t minus 18. Well, it's a linear function, so we know it's going to cross the x-axis only once. So let's just solve for it. We have 0 is equal to 6t minus 18. That gives us 18 is equal to 6t. And that gives us that, so I was going to say 6 is equal to 3. T is equal to 3. So that means at 3 is the only chance it has to switch from positive to negative. And we know it's linear. Actually, let's still just do it just for technical purposes. We can, at I'll say it like this. At this point, maybe you should be able to clock that's going to be negative here and positive here from the right. But let's just do it as good practice. It doesn't really hurt. Okay, so from the left of 3, let's pick a value. Let's pick 1. So it's going to be 6 times 1 minus 18. 6 minus 18, that's going to be negative 12. And then A, let's do 4. 6 times 4 minus 18. 24 minus 18, that's going to be 6. Positive. So now we have we have all the work done, but now we just need to do oh, I hit the camera by accident. But now we just need to do the pattern solving. At what time intervals is the particle speeding up or slowing down? So remember, speeding up is when both values of the function are matching. So they're both positive or they're both negative. Now we see here in terms of speeding up, we see that they only share the same positive or the same values, not positive, the same values from 2 to 3, and from 4 to 5. So right here from 3 to 4, this is still negative. Here it's positive, and then right after 4, it's positive and positive. Keep in mind, we don't include 4, and we don't include 2, and we don't include 3, because at 2, the velocity is 0. At 3, the acceleration is 0, and at 4, the velocity is 0. And we care about their signs, and we know that their signs at 0 are neither positive nor negative. So that's just for speeding up. Slowing down means that they have two alternate signs. So we see from 0 up until 2, they are alternating positive and negative. And then as soon as we enter 3, so from 3 to 4, wait, give me a second. I think I messed up. I stopped at 5, but technically it goes on to infinity. That's a typo, my mistake. I don't know why I stopped at 5. I think I just mentally saw 5 and stopped there. For slowing down though, we see that it only happens where they have alternating signs in between 3 and 4. So 3, comma 4. And that's going to be slowing down. All right, this wraps up day 2. Let me know if you guys have any questions. Sorry for that last hiccup. I will see you all in the next video. Bye-bye.